I just kind of free talk, but this is a lot of stuff in terms of trying to cover regarding like which metabolites and which ATP, citrates, and all of those things. So I'm going to start off with obviously telling the camera as well. I mean, I'm only going to be going up to slides like 1 to 36 maybe, 1 to 36. So I skipped the last like 3-ish slides on Phosphorylation, which is actually very easy. And it's not easy. It's just not that bad to understand. Like, it takes a little bit of time, maybe. And I'm not going to go over glycogen degradation or synthesis. It's too much information. I cannot cover all of that, and that's just not going to be enough time. So what I am going to talk about are the first 3 points: explaining general methods of regulating the flow of metabolites, understanding why AMP is a potent regulator of cellular energy needs, and then giving an explanation of hexokinase, PFK1, and then pyruvate kinase. So what I'm going to do is first is kind of briefly talk about how when we talk about gluconeogenesis and we talk about glycolysis, obviously they're reversible processes, right? But the whole important part here is that they aren't quite the same. Obviously you have steps 1, 3, and 10, which have to do with glycolysis. Those are the main point regulators. Remember, step 1, you have to phosphorylate glucose to keep it inside the cell because you don't want it to leave. Step 3 is when you actually commit to glycolysis, right? We say PFK1, that's good, right? And even in her slides, PFK1 is something where we see it be regulated by like a lot of other compounds, right? We see it regulated by fructose 2,6 bisphosphate. You see it regulated by ATP, citrate, ADP, AMP. So you see there's a lot of regulators regarding that one enzyme in step 3. And then of course you have pyruvate kinase. Nothing too bad on pyruvate kinase. I think it's pretty simple. Again, it's all about what's happening to the enzyme. Are you activating it or are you inhibiting it? As soon as you activate an enzyme, it's probably going to do the process it needs to. As soon as you inhibit it, right, with those factors of ATP, ADP, and stuff like that, then you'll stop it, right? So what I'm going to talk about right now is glycolysis and gluconeogenesis. They happen in different parts of the body, right? You have glycolysis happening in your brain, in your muscles, and you have usually gluconeogenesis happening in your liver, your kidneys. The reason why they're in different spots is for efficiency, effectiveness, right? You're not going to see 2 processes happen in the exact same spot. It's ineffective. I mean, you don't want to be using the energy that you need for glycolysis and then spending it on gluconeogenesis, right? They have to be separate. They have to be regulated, right? And this is all about homeostasis. As soon as I upregulate one pathway, you're probably going to be downregulating another pathway. And I'll give you an example right now. If I have an increase in ATP, do you think glycolysis is going to happen? If I have a lot of ATP, yeah, glycolysis won't happen. In fact, you're probably going to do something else. Maybe you'll do synthesis of fatty acids. Maybe you'll do synthesis of proteins. I don't know, but you're definitely not going to be catabolizing glucose, right? This is the idea of catabolism and anabolism, right? Anabolism usually uses energy to make something. Catabolism is the idea of breaking something down to yield energy, which is exactly what glycolysis is, okay? Let me give you a quick example, right? Do you guys know what the adrenocorticotropin hormone is, ACTH? Have you heard of it, maybe, right? So, if you have, I'm just giving you an example so you can see it, right? If I have an increase in ACTH, this is made in your adrenal medulla, actually, and it's activated by corticotropin releasing hormone, which is made in your anterior pituitary. So I'm talking about your anterior pituitary, your hypothalamus, okay? Yeah, I'm right. So what's happening here is that as soon as your body, right? As soon as you get this adrenocorticotropin hormone, what's happening here is that you're going to increase your cortisol levels. When you hear about cortisol, what does that mean? Stress, exactly. And if you have high stress, usually that's indicative of low blood glucose levels. So it's saying that your VGL, right, is low. So what's going to happen here is that you need to increase that. So you'll gluconeogenesis will start happening because you want to make energy, right? That's what stress means. And then obviously, if that happens, you would be inhibiting glycolysis. That's just an example I wanted to show you. Okay. Now, the next thing I'm going to talk about here, remember I have this here because it's a bunch of stuff, okay? Feedback inhibition. Do you guys understand what feedback inhibition is, right? Right now, I'm going to be discussing ways that you regulate metabolic flow. When we say regulate metabolic flow, it's the same idea as do you turn on which enzyme, how do you turn it on? The ways to turn on, the ways to turn off are feedback inhibition, enzyme activity, and the rate of a biochemical reaction. So let's real quickly go through the first one. Can anyone tell me what feedback inhibition is? Just say it and I'll listen. Feedback inhibition? Do you guys know what it is?
Was it when something is produced, it restricts more production of that thing?
Yeah. So we're saying that, for example, I'm just going to use A and B and C as a good indicator. So let's say I have A makes product B. Let's say product B will make product C, and we'll say it makes product D. Right? And this will be enzyme 1, enzyme 2, enzyme 3. Let's say if I effectively make a lot of product D, if you make a lot of product D, what can happen here is feedback inhibition. It tells maybe enzyme 1, stop doing this process, I already made enough of D. That's what it's saying, right? So like you said, if I make a lot of this product, maybe I'll stop this enzyme here. Maybe if you make a lot of C, it'll stop this enzyme here. What I'm saying is that too much of a product can cause inhibition of the enzyme prior to it, okay? Let's give you an example of glycolysis. So, pyruvate kinase, which step is that in?
Last step.
Yep, last step. So if I know that this is pyruvate kinase, so what's the product, what's the reactant?
The product is pyruvate. The reactant is phosphorylation.
PEP. It's PEP, right? So you're going to be making a lot of ATP, right? Because that's this step. ADP plus PI. How do you think pyruvate kinase would be regulated? This is a really good example of feedback inhibition. Think about the steps before it, okay? Think about the 9 steps before this. Think about it. What do you think could stop PEP from going into pyruvate? What do you think could stop it?
Oversaturated ATP? Like
Yeah,
ATP?
yeah, a lot of ATP. If, like, for example, in step 7, you know step 7 also makes ATP, right? The enzyme, I'm going to write it, is phosphoglycerate. It's phosphoglycerate kinase, right? You make ATP in this. If I have a lot of ATP, then you will not be seeing this reaction happening. No, it doesn't happen, right? But what's also important to recognize is, what if, how could you also push this reaction forward? So you told me how to stop it, right? If I have a lot of ATP, then what do you think could push the reaction forward? So let's reverse this and say, I actually want to make this happen. How do you think you could do that? What do you think would allow for this to happen? Increase in PEP, yeah, so increase in PEP. But more importantly, increase in fructose 1,6-bisphosphate. Write it down. If I have an increase in fructose 1,6-bisphosphate, I'm not going to write it all out. What step do you make fructose 1,6-bisphosphate in? Think about it.
Step 3?
Step 3?
Yeah.
Yep. Right after PFK. Right? You use the enzyme PFK to make fructose 1,6-bisphosphate. If you have a lot of this product, right? If you have a lot of this reactant in this case, because it's prior to pyruvate, then you're going to continue pushing until you get to PEP, which makes pyruvate. Does that make sense? The idea that you can accumulate all the products in prior steps, right, which can activate this pathway. In particular, the one that we tend to focus on is fructose 1,6-bisphosphate. Another thing that we can say is increase in AMP. Do you guys understand what AMP is? So, how I like to think about it is that if I have a lot of ATP, if you have a lot of ATP, that means you have very low AMP. If I have a lot of AMP, then that means I have very low ATP. So what am I telling you? I'm saying that if AMP is high, that's basically saying, that ATP is low. And what does that tell you? If ATP is low, you're going to go ahead and activate that enzyme, pyruvate kinase. Do you see how different modulators, right? The idea of feedback inhibition with this, right? This doesn't inhibit though. This actually activates it. But for example, if I have too much pyruvate being made, then you won't be seeing this happening, right? If I have too much of product, this enzyme doesn't get activated. It doesn't work like that. That's feedback inhibition. You have too much building up here, I'll stop the enzyme from happening. I already have enough, there's no point. But I have modulators like this, AMP, and obviously ATP, right? That can say, yeah, go ahead and do it. What you need to get engraved in your head is, if I have a lot of AMP, that means there's low ATP. If I have a lot of ATP, then that means there is low AMP. I'm going to go through it in a second, but this is just an example I wanted to give to you. So the next thing that Dr. Erb kind of goes over is you can modulate enzymes also by phosphorylating and dephosphorylating. And I'm pretty sure you see that not only with glycogen phosphorylase, right? Even though I'm not going to go over glycogen, it is an enzyme. And you can activate it by either phosphorylating it, and then of course deactivating it by dephosphorylating. But do not think that just because you phosphorylate something, it's activated. It can mean it's also being inactivated. If I dephosphorylate something, that doesn't mean it's just going to be inactivated. No, it could also mean it's activated for certain enzymes. So do not mix it up on your exam that if I phosphorylate glycogen, that means inactivation. Well, in that case, it actually is activation. Okay? So, phosphorylation, dephosphorylation of enzymes can either inhibit or activate enzymes to do the further processes. Give me 1 second, I want to look at the other stuff here. The other way, obviously, we talked about feedback inhibition, too much product, stops an enzyme. The other thing is that, remember Le Chatelier's rule? The idea that if I have a lot of reactants, you're going to push forward. That's the same idea. If I have a lot of substrate, if I have a lot of reactants, I'm going to go ahead and push the reaction forward. I can continue it. There's enough, right? You want to de-stress your reactants and push to the next side. Push the reaction forward, right? And we do this by, you guys remember in glycolysis how some of those mechanisms were positive, right? Right? Delta G was positive. When delta G is positive, what do we think?
Unfavorable.
Unfavorable, right? So how do you make it favorable?
Making there more products, or making there more reactants than products.
Yeah, exactly. You make more reactants than products. And the way you do this is that every time, for example, if I have A going into B by enzyme 1, okay? What I can do here, let's do something even better. Let's go ahead and do, let's do 2-phosphoglycerate, and let's say it will go into Keq, and this is by enolase. H2O leaves. Okay, this is step, I believe, 9 of glycolysis. So what we can say here is that, yes, you're right. If I increase the amount of reactants, I'll push the products. But the idea here is that if I can continuously keep this low, and what that means is push this next thing into pyruvate, right? Then obviously the reaction will continue moving forward, right? We're saying that the way to keep this low is to automatically just transfer to the next thing. You're trying to transfer as fast as you can so that the reactants are continuously accumulating, right? And that's how you can you can counteract the actual delta G that's positive, or no, the standard delta G that's positive, and make the actual delta G negative, right? Do we kind of, yeah, make sense? That was kind of fast what I said. Okay, so we talked about enzyme activity, right? Phosphorylating, feedback inhibition. We talked about how delta G, right? So what if I tell you that you can also have regulatory proteins? What are regulatory proteins, if anyone knows by any chance? So what a regulatory protein is that it's something that binds to the enzyme. And what it does is that it allows for the catalytic activity to happen. So let's say this. Actually drew a little picture too. You know that enzymes are activated, right? Or they have a lot of substrate around them which allows them to be activated, right? When we say regulatory protein, we'll say something like this. Let's say we have, this is our enzyme, okay? We'll call it enzyme. And maybe it has a scaffold, so it needs to attach to something. We'll say like this is our scaffold, right? Scaffold. And we can say this is like a subunit, right? It's just a random subunit. Two things just need to combine right now, okay? When we combine these two together, okay, what's gonna happen is obviously it'll look something like this maybe, right? So I have my enzyme in this scaffold. It's not protected, it's just you made another unit. You needed this unit so that you can create a hollow enzyme. Do you guys know what a hollow enzyme is? So a hollow enzyme is what we call an active enzyme, meaning that you've put all the parts together of this enzyme to activate it. You see right now, this is just an enzyme on a scaffold. It's not a hollow enzyme yet, meaning that we haven't activated the enzyme to do its job. So what we can do here is add the regulatory protein. Let's say the regulatory protein is something like this. Right, I'll call this my regulatory protein. As soon as I add this regulatory protein onto here, right? Now, this is going to be called a hollow enzyme, meaning that it's activated. It's an activated enzyme. There are also things called apo enzymes, or something like that. That's just the opposite of it. Apo usually means without something, so that's just like a prefix. Hollow enzyme, as soon as you add this regulatory protein onto this enzyme, you've activated it. So you got regulatory proteins, you have phosphorylation of enzymes, you have feedback inhibition. All of these things are regulating enzymes, and indefinitely it is regulating homeostasis and metabolism, right? You controlling enzymes means you control metabolism, okay? So that's that, okay? I've kind of covered everything. Let's see if I have a little bit more left. Everything else is very self-explanatory. She says, changing the rate of a reaction, aka, if you keep the reactants high, you can push forward. If you keep the substrate low, what do you think happens? If you keep substrate low, it's probably not going to go forward, right? Yeah. I didn't know if you guys were going to catch on to it. Okay. Is there anything that I need to go over up until now? Is there something in the PowerPoint that is confusing you that I should know of? If you have the PowerPoint open by any chance? Okay, so the next thing I'm going to talk about, again, just kind of briefly hitting her slides in case there's stuff that are confusing. Ooh, this is actually a little bit interesting. Reactions that are far from equilibrium. What 3 points of glycolysis are going to be far from equilibrium?
1, 3, and 10.
Yeah, 1, 3, and 10. Do you know why?
They talking about ATP.
Yeah, honestly, it's actually because they just have to push the reaction forward. That's how you do glycolysis. If they were reversible, you'd be kind of going back and forth between the product and reactant. You're never actually going to get anything done. So that's why you push it. It's the first step, the last step, and then the commitment, step 3. So what she's saying here is that most reactions are actually going to be reversible, right? You're not going to have a delta G that is very, very negative, okay? But in 1, 3, and 10, they are negative. But notice, they're not so negative. It's not like negative 9,000 or something like that. It's like negative 30, negative 15, negative 17. These are low delta negative G values. The reason why we keep our delta G negative, but not too negative, is because there are times in metabolism where, I'm not saying this is likely, and this is just what I have written from her lectures and stuff. She mentions that there are times when, obviously, there will be, maybe you'll have to actually go backwards, right? And if you think about it, if your delta negative G is way too high, right? It's really, really high, so you're definitely going to be pushing forward. It's going to be very hard to counteract that and go backwards. Do you notice that if something has a very, very high delta negative G, you know, if you like switch it when you're doing reactions, the delta G, the positive one, is very, very high, meaning that it takes a lot of energy to go back this way as well. So if you keep a reaction negative, so yeah, it's favorable, but not too negative that you can't actually go backwards if you really, really need to, then you're fine. So I guess it's kind of counteractive, or counter to like almost everything that we've learned so far, that delta negative G is always going to go forward, but the body's complex. So there will be times where you need to go backwards to your starting point. And the reason that we try to keep delta negative G low is because if it's too negative and you have to go backwards, that essentially means you have to put in a lot of energy. You're going to have an opposite positive delta G that's very, very high. But at least if it's still negative a little bit, and then you switch it, and it's just a little bit positive, you can do it. Are we good with that? I really briefly kind of went over that slide. I believe it's, I don't know what slide it is actually, I don't have it written here. But that was my point. We're good? Do you guys understand that slide? It's slide 18.
No.
No? Okay. Is it okay if I can just briefly explain it to you? I mean, I don't actually think it's that hard. I think people get confused when they look at it. The whole thing is that you're kind of comparing the Keq and the mass quotient, Keq and the mass quotient Q. You guys know the difference between Keq and Q? Yeah? I mean, yeah, I'll tell you again. So remember in last unit, Keq is what are your products and reactants at equilibrium. Q is just telling you what's your products and reactants at any point in time, okay? When we talk about something at equilibrium, especially for Keq, it's a little bit different from mass quotient Q. So it's going to tell you two different things, actually. So I'll explain to you. Look at hexokinase, okay? They are telling you, I have it pulled up as well, they're telling you your hexo, I'm going to write it as HK. They're telling you that your Keq is, what is it, 1 times 10 to the third? And then, let's look at your Q for the liver. So they're telling you mass quotient Q is, I think, 2 times 10 to the negative 2. Keq is also correlating to this value right here. It's correlating to this, right? We know that Keq usually has to do with the standard, so that's why we have that. So it would be negative 17. And then, of course, we have delta G is around negative 27. Oh, it's only giving the hard, but that's fine. Delta G is negative 27, right? So I kind of wrote down these stuff for you. Can I ask you a question? Why do you think, if you look here, okay, good. It says when your Keq is 1 times 10 to the third, it's basically saying, I'm going to put this down here real quickly. It's saying that, obviously, Keq is products over reactants, right? It's saying that 1 times 10 to the third basically means this. telling you at equilibrium, you have 1,000 products over reactants. It's just telling you at equilibrium we're pushing to the right. Okay, we're pushing to the right, we're making products, which is why your delta standard is negative, right? Let's even make that a little bit better. Okay? Now, you understand this. KEQ though, is a little bit different. And this is kind of a trick question, so just stick around, okay? So if I have Q is saying, well, it's 1 over 200. It's telling you that your reactants are at 200, your products are at 1, your delta G, your actual, is negative 27. So this is actually a little bit different. When you talk about mass pushing Q, you're usually comparing it to the the KEQ, and that just has to go back to Gen Chem 2 stuff. I kind of went over it in a lecture regarding free energy. But what this is saying here is that your reactants are at 200, so if you have a lot of 200, right, the reactants, and your products are 1, it's saying here that if you have a lot of reactants, continue pushing and making more, which means that your actual is going to be negative 27. Does that make sense? It's opposite. It's really different from what I just said about KEQ. If you notice, did you notice what was different? In KEQ, I told you that it was 1,000 over 1. But I told you that it has a lot of products, right? And it's saying that at equilibrium, you're shifting to the right, correct? And then I told you for Q that you have a lot of reactants, but you're shifting forward. So, do you guys understand, right? Like, there's a big difference from what I just said. So you're not losing anything. You're not confused. It's actually how it is. It's saying here that when you're at equilibrium, you know that this value is usually getting compared to 1, right? So KEQ, 1, KEQ, 1, and then obviously KEQ equal to 1, right? This is just telling you about delta G. When you look at KEQ, it tells you about your standard delta G. Obviously, what it's saying here is that when KEQ is greater than 1, right, which is exactly what it is, right? KEQ right here is 1,000. If it is greater than 1,000, if 1,000 is greater than 1, you shift to the right. That's what it says. When you talk about Q, Q is different. Q is actually not getting measured to 1. It gets measured back to KEQ. Let me show you. Now, for Q, it's actually a bit different. Q says that if Q is greater than KEQ, and Q is less than KEQ, right? And obviously there's an equal one as well, but I'm not going to write it at the moment. This is a little bit different, okay? I'm going to show you with this. So let me show you here. Here what it's saying, it's comparing the concentrations of product and reactant at equilibrium and product and reactant at some random time, and that's Q, right? So if Q is less than KEQ, so let's say it's 1 over 200, right? And we'll say that at equilibrium it's 1,000 over 1, right? Let me ask you a question. If at equilibrium you're at 1,000, and at some point in time, okay, your reactants are at 200, what direction do you think you're going to shift? Just think. What direction do you shift in? This is always the hardest thing for me to teach as well, because I think people get confused with this relationship at times. Just think while I think of a way to properly explain it to you. Left? No.
Then it's to the right.
Yes. It's to the right. It's because, let me formulate it myself so that I don't say anything wrong and it gets more confusing, because that's not my job. Let me think how I can explain it better to you.
Same thing. So
Yeah.
if you're saying at equilibrium you have really high product,
Yeah.
the whole idea is to favor equilibrium. So we are
Thank you.
forming.
Yes.
Well,
Yeah, You wanna come up here and explain it? No, yeah, okay, yeah, yeah, that's a good way of explaining it. Yeah, okay, so.
Go ahead.
All right.
What you said.
So what Sophia said is that if you were to, since it's the Keq, right, and you know that your Q is 1/200, you're always trying to approach equilibrium. And the idea of approaching equilibrium, generally speaking, if Q is lower than Keq, means that you need to get there. So you need to increase to get there, meaning that you need to accumulate more products, obviously, which is the whole reason of having a negative delta G value. Did that make sense? Okay, good. We're done with this. I'm not going to even touch it anymore.
I
Okay.
have a question.
I'll just maybe go over it here too.
You saying we need to know the KEQs or the
No.
relationship?
The conceptually speaking, what I just said. Yeah.
The relationship.
The relationship, not even the greater than or less than. Just I think the idea that you have Q and you have KEQ. What's going to happen? What is associated with which? And just the idea that different enzymes work at different KEQs and different Qs, just to drive a reaction forward.
But you didn't have to know any of these numbers.
No,
Okay.
just conceptual, yeah.
Great.
I have like 15 minutes left, so what I am going to do is really quickly talk about AMP, and I'll probably only talk about hexokinase and PFK, because I did technically talk a little bit about pyruvate kinase, about how it's activated by lots of levels of fructose 1,6 bisphosphate, and if you obviously have a lot of AMP, right? Because if you have a lot of AMP, what does that mean about ATP? You don't have a lot of ATP. Okay, so really quickly, hexokinase, actually, we'll talk about AMP real quickly. Yeah. So the relationship of AMP is like this. If AMP is high, then that means that ATP is low, right? So that means that you have to start building processes, you have to start doing pathways to get this to increase, because right now it's telling you that it's decreased. So what this thing, AMP, is going to do, okay, it's going to activate this thing called AMPK kinase, it's AMP kinase. And what this thing does, what this kinase does, is that it triggers a bunch of metabolic processes. So we'll write right here, it triggers metabolic processes, okay, to basically eventually increase ATP, right? So AMPK triggers metabolic processes in order to increase ATP. What process do you think is gonna do it?
Glycolysis?
Yeah, glycolysis. What processes do you think? So I'll put a plus sign because it's happening. What processes do you think it inhibits them?
Glycogenesis?
Yeah, gluconeogenesis. Yeah.
That makes sense.
Give me one more.
I don't remember.
Fatty acid synthesis, right? Synthesizing anabolic reactions are going to be deregulated when you're upregulating catabolic reactions. Remember, catabolic creates energy, anabolic uses energy. Anabolic has to do with synthesizing, catabolic has to do with breaking down. So you're going to stop synthesis, anabolic reaction of gluconeogenesis, and you'll stop cholesterol fatty acid synthesis. All right, FA synthesis, right? So these two things do not happen, but glycolysis would happen. Okay? That's just the general mechanism of AMPK and what its objective is in all different parts of the body. So brain, skeletal muscles, glycolysis, gluconeogenesis, fatty acid synthesis wouldn't be happening in mammillary glands like adrenal cortex, or gluconeogenesis like in the liver or kidneys. Okie dokie, that was really fast. So you can see now how this is a potent regulator, right? How if you have a lot of it, it means that, and if it's the opposite, then you would be doing these. Opposite meaning that low AMP means high ATP. If you have a lot of ATP, then you could probably actually put it into gluconeogenesis and fatty acid synthesis, because anabolic reactions require energy. Good? Okay, let me know if I lost anybody. Let's do hexokinase real quickly. Okay, does anyone know what hexokinase is? Just that, you need to know that there's 4 isozymes, right, of hexokinase, meaning that I have different versions of hexokinase that catalyze the same reaction. An isozyme is basically an enzyme that is a different type of enzyme, maybe structurally a little bit different, but catalyzing the same reaction. So hexokinase, okay, has 4 enzymes. We have 1, 2, 3, and 4, right? Hexokinase 1, you can find anywhere in cells, right? And it functions at pretty low glucose levels. Then you have hexokinase 2. Let me write it down real quickly. I'll have hexokinase 2, right? And of course I have, this is going to be in the muscle cells. By the way, it's recording still, right? Just want to make sure.
Yeah.
Okay. It's in the muscle cells. And then I have hexokinase 4. This is really important because it's also known as, aka glucokinase. Why do you think it's called glucokinase? It's okay. It's called glucokinase actually because it's found in the liver, right? So this is found in the muscle cells. This is found in the liver. And it's called glucokinase because it has a very different function actually. So in glycolysis, let's take a step back. Actually, give me a second. I wanna you look at this for a second. Just think about it, and I'm gonna draw a picture real quickly and make sure my picture's good. Okay, so hexokinase 2 versus hexokinase 4. Before I write the rest of it, I'm going to tell you that this functions at low Km values, and this functions at high Km values. What do you think I mean by that? When I tell you that hexokinase 2 is functioning at low Km, and I tell you that hexokinase 4 is functioning at high levels.
The amount of glucose that they have is under or above 50%.
Yeah, exactly. I'm telling you that your hexokinase 2, just me being alive, right? This hexokinase is working at low levels of glucose, meaning I can take as much glucose, whatever, right now, and I can start doing whatever process I need to do with hexokinase. We know hexokinase is used in step 1 of glycolysis, so let's go ahead and write it real quickly. Hopefully, yeah, I hope it works. So we'll see glucose, right? Goes into glucose 6-phosphate via hexokinase 1, and we're in the muscle cells right now, right? It's saying here that obviously low levels of it, I'm gonna use it, I'm gonna go through it, right? But you guys do realize that if you have too much G6P, too much glucose 6-phosphate, do you think this reaction will happen? No. Feedback inhibition, right? If there's too much G6P, we're gonna inhibit hexokinase 1 in the muscle. That is very different for hexokinase 4. Hexokinase 4 is found in the liver and it works at a high Km, meaning if I just ate a very high carbohydrate meal and my blood has a very high blood glucose concentration at the moment, let's say 15 millimolar or something, because usually your blood is like around 5 millimolar. 15 millimolar is pretty high, it means you just ate something, right? If I'm functioning at 15 millimolar, we're gonna start seeing hexokinase 4 start working. Why do you think we start seeing it work? Do you guys remember GLUT2, the transporter? I believe it's GLUT2. I could be wrong. I'll go ahead and edit it if I need to. GLUT2 transporter, you guys know that it also works at high Km values, right? It's saying that I will only take in glucose if I eat a very dense carbohydrate meal. I'll bring it inside, okay? And I'll do whatever I need to do with it in the liver. Well, what do you think you're going to do with it in the liver? You're going to use glucokinase, right? What glucokinase is going to do is it's going to take all that blood glucose that went through the GLUT2 transporter, it's going to take it inside, and you're going to do the exact same process. Remember, these enzymes are catalyzing the same reaction. It's just a different version of it. So in the liver, what we'll see is, so use a different color. In the liver, what's going to happen is, again, you're going to see glucose go into glucose 6-phosphate, and you're going to use hexokinase 4, right? You'll use this. But this thing doesn't do glycolysis, no. with it, because you know that the liver stores glycogen, right? Do you guys remember glycogen synthesis? Right? Glycogen synthesis, to actually start it, you need to get glucose 6-phosphate, right? Because you need to trap it inside the cell. Glucokinase is going to trap it, right? The same way hexokinase traps it, right? Because you add a phosphate to it. The thing here is that while this goes on to glycolysis, this one can go into making glycogen instead. You'll do glycogen synthase. As soon as you get glucose 6-phosphate, you can actually get glucose 1-phosphate. Remember glucose 1-phosphate? It's the beginning, the starting steps to do glycogen synthase. You should remember this. Glucose 1-phosphate is very important. You actually use this compound called phosphoglucomutase, I believe. If I'm wrong, I'll edit it, but I don't think so. It's phosphoglucomutase. And really all it does here is that as soon as you have G1P, you can start doing glycogen synthesis. That's what it's saying here. It's telling you, get the glucose, as much glucose as you can, bring it inside, phosphorylate it with hexokinase 4, right? Because you're at a high Km right now, you're gonna phosphorylate it, you get G6P. You're not gonna do glycolysis in the liver, it doesn't make sense. Glycolysis does not happen in the liver. You can make glycogen, right? You can store it instead, because remember, we have a lot of glucose, we don't need it right now. We just ate, you're not running a marathon, okay? You're gonna go ahead and store it. The way to store it, synthesizing glycogen. We'll take G6P, use an enzyme called phosphoglucomutase, and all it does is it takes the phosphate that's on the carbon 6 and it puts it on carbon 1. And then from there, you're gonna go ahead and do glycogen synthesis. Does that make sense? What I just did? Okay, cool. Now, one thing that I feel like it was on the tip of my tongue, worth mentioning. Well, if it's not on the tip of my tongue anymore, I guess it's not worth mentioning. But we get it? Yeah, we're good? Okay. Wow, what was I gonna say?
The regulations of hexokinase 4?
Cool. Yes. Okay, listen. So, thank you. You know how I told you that if you have too much glucose 6-phosphate, it inhibits hexokinase. Whoa, this should be 2. My bad. Because we're talking about 2 in the muscle cells. It inhibits this enzyme. That does not happen for glucokinase. It does not. Because if you think about it, you're not actually doing glycolysis. So there's no need to inhibit anything. In fact, you're doing glycogen synthesis. So even if you accumulate so much glucose 6-phosphate, it doesn't do feedback inhibition on this. Okay? You're just gonna continue going and you're gonna continue storing. Do you get my point now? Right? Feedback inhibition happens here, but it doesn't really happen here. Because what we're saying here is that we're not gonna do glycolysis, we're gonna go ahead and do glycogen synthesis. There's nothing wrong with storing. Like, you're not doing anything really crazy or anything like that, you're just storing. Does that make sense? I don't have a lot of time, and I really want to talk about phosphofructokinase because I think that that's actually the hardest thing because it talks about fructose 2,6-bisphosphate. Can I ask you a question? Can I talk about PFK1 real quickly? It's going to be pretty fast, okay? Yeah, I'm going to make it as fast as I can. You guys know what step is PFK1? Yep, step 3. Okay. There's an easy way to actually remember this stuff, and I'm going to show you right now. Maybe you can take a picture of it and like remember it for your exam or something, and then I can go, as long as you understand what I'm about to write, then you should be fine, okay? PFK1, okay, is going to be regulated by ATP. You know what, why don't I just draw it actually? It makes more sense to you. So, you'd be going from fructose 6-phosphate, right? You can go this way, and you can make fructose 1,6-bisphosphate. Sorry, I know this is a really bad way of saying, but fructose 1,6-bisphosphate. Obviously, use PFK1. How do you think you activate this pathway? Think about it, just generally speaking. Don't look at the slide and tell me. Yeah, but I'm talking about actual regulators. I'm talking about modulators. So maybe if there's high AMP, you'll go ahead and do this pathway, right? What's another one?
Low ATP.
Because remember, whoa, that was bad. If you have high AMP and low ATP, you're going to go ahead and do, this is glycolysis essentially, right? Give me at least one more. What can stop this pathway? Citrate? You guys know what citrate is? If you have a lot of citrate, let me tell you right now, ATP and citrate are basically the same thing. They are very high energy carriers, not carriers, they're high energy substances. When you see citrate, that usually has to do with the citric acid cycle. It means that you already made ATP and glycolysis and you're going into the citric acid cycle. That's enough to tell you that you're going to go ahead and make energy because, well, you'll see it in the next slide or in the next module. Citrate in the citric acid cycle is going to evidently go into isocitrate and then it continues going and you make more and more ATP. So think about it. If you already have a lot of citrate, okay, it's telling you that you don't need to continue making ATP because all of that citrate can continue going down to electron transport chain. Does that make sense? It doesn't say it. Does it not make sense?
It's enough.
Enough? I mean, you'll see it probably next week what I'm talking about. But just understand that ATP and citrate are almost the same thing. It means that you have a lot of energy, okay? It's saying that if you have a lot of citrate, right, that means that you're far enough along the pathway to making energy, right? It's like saying that if you have a lot of pyruvate, do you think you're going to continue making ATP? Do you? No, you're not, right? The same idea that if you have a lot of citrate, do you think you're going to continue making a lot of ATP? No, because that is already telling you you have enough of those products to continue making. There's no use to making more of them. It's the same thing as saying that if you have a lot of ATP, do you think you're going to continue making those processes? No, you're not, right? Do you guys see where I'm going with this? So, if you have a lot of citrate, if you have a lot of citrate, you're not going to do PFK1. It inhibits this enzyme. If you have low ATP though, you're going to go ahead and make it. If you have high AMP, you're going to go ahead and activate PFK1, right? Because the idea is that if I have a lot of AMP, that means low ATP, right? Okay. Now, there's another part though, right? Because we go this way, we do gluconeogenesis, right? GN gluconeogenesis. So what does that mean? That says that if I'm going this way, right? What do you think would activate? I'm going to write it a little bit differently from the slides. It's called fructose 1,6 bisphosphatase, okay? Fructose 1,6 BPase, I call it like that. What do you think, okay, would inactivate this pathway? How do you stop from going from gluconeogenesis? This, right? Like if you have high AMP, then you're not going to do this reaction, right? If you have low ATP, you're not going to do gluconeogenesis. If you have a lot of citrate though, it's saying you've got a lot of energy already happening, so go ahead and do a different process. We already got energy down the line. Don't worry about it. Go make something else. It makes sense, right? Alright, now I'm going to talk about the regulation of PFK1, because this is important. This thing here, that's why you talk about the commitment of glycolysis, okay? Erase it. PFK1 is regulated by a compound called fructose 2,6 bisphosphate. Fructose 2,6 bisphosphate is not found in glycolysis. It's not found in the citric acid cycle. It is actually made just to regulate PFK1. So you can imagine how important it is if it's only being made to regulate something, right? So let's do this, okay? So you need to know how to make fructose 2,6 bisphosphate first, okay? How you make it is like this. You're still starting with You know how fructose 6-phosphate uses PFK1 to make fructose 1,6-bisphosphate in glycolysis? Well, this thing is going to use, what do you think? It's going to use PFK2, and it's going to make, what do you think? Fructose 2,6-bisphosphate, okay? There's not a really big difference here. If it was PFK1, you would just see this with a 1 here. But it's PFK2, so it's telling you phosphorylate carbon 2. That's why it's called fructose 2,6-bisphosphate, using PFK2. So if you phosphorylate this thing, aka you use obviously ATP, go into ADP, plus PI, right? You can make a lot of this. Now there's an opposite though, right? What happens when you have fructose 2,6-bisphosphate and you want to go into fructose 6-phosphate? What enzyme do you think you would use here? It's not much different from what you see in gluconeogenesis. Just add a 2, guys. Fructose 2,6-bisphosphatase. The same idea in gluconeogenesis, step 8, right when you're at the top, right? You remember you go from fructose 1,6-bisphosphate to fructose 6-phosphate, right? Because you're going backwards, gluconeogenesis. And you use the enzyme fructose 1,6-bisphosphatase, right? A phosphatase takes off a phosphate, right? The way to take it off is add water, and the PI, the phosphate comes off, right? Okay, this is the same exact thing. You just have to change this number to a 2. Are we on the same path? Like, these things are not very different from each other. So now you can see that this is obviously going to lower your fructose 2,6-bisphosphate levels, while this one would increase your fructose 2,6-bisphosphate levels. You got it, right? You see it? You see that these two enzymes are basically going to tell us, these are going to tell us how much you're getting, right? If you break something down, you're not going to have a lot of it anymore. If you are making it, then you're obviously going to increase the amount of it. What you need to understand here is that if there's an increase in fructose 2-bisphosphate, you're going to activate PFK1. Right? And what? If you decrease the amount of it, so this is increase fructose 2,6-bisphosphate. If you decrease fructose 2,6-bisphosphate, then you're obviously going to stop or inhibit PFK1. Get that just down. Just get that down. If I have a lot of fructose 2-bisphosphate, I will activate PFK1, meaning I will do glycolysis, right? Because if you activate an enzyme, you're going to do the process. If you lower the amount of those levels, then what do you think happens? You're not going to be using PFK1, meaning you're not going to really have glycolysis. So let me ask you this then. If I have an increased amount of PFK2, will PFK1 be activated or inhibited? If I have an increased amount of this enzyme, PFK2, will glycolysis, or should I say, would PFK1 be activated or not?
Would be activated.
It would be activated, right? Because PFK2 is telling you that you're going from fructose 6-phosphate to this. If this enzyme is actually making this product, right? And I told you fructose 2,6-bisphosphate is an activator of PFK1, then obviously PFK2 can activate PFK1, right? Does that conceptually make sense, right? Because PFK2 is increasing these levels, and increasing these levels means activation here. It means glycolysis. PFK1 activated means you're going to continue glycolysis. You committed. But now let me ask you, if I have fructose 6-bisphosphatase, if this is activated, you think PFK1 will be activated or inhibited? Inhibited, yes, it's inhibited because if you lower, what's happening here is that you're breaking it apart. You're lowering the amount of fructose 2,6-bisphosphate, meaning that you're making fructose 6-phosphate. This activator's not here anymore. If the activator's not here, you're not going to have PFK1 and you're not going to do glycolysis. Instead, you would do gluconeogenesis. Okay? LOL. I'm just being serious with you. And this is my last thing and I'm done, I swear. When we talk about PFK, and we talk about this thing, fructose 2,6-bisphosphate. It's an enzyme that looks kind of like this. It's like a peptide kind of chain, two of them on the same thing. Right? You'll have PFK2 here. You'll have fructose 2,6-bisphosphatase, and then you'll have PFK2 here, and you'll have fructose 2,6-bisphosphatase, right? So.
Are these the hollow enzymes we talked about earlier?
Enzymes. So the thing is that a hollow enzyme is a little bit different from phosphorylating and dephosphorylating something. So what's happening, I'm doing here is showing you phosphorylation and dephosphorylation to activate something. Usually a hollow enzyme, in the case of this, would have to do with regulatory proteins. So these aren't really regulatory proteins, it's more so phosphorylation and dephosphorylation. So, what's happening here is that, so you see, PFK2 is being, this is a little bit nitty-gritty, and I saw it in the slides. Do you understand that slide that I'm talking about right now? If you have it open, can you tell me what slide it is? Because I don't have that slide number.
32.
It's what? Which one?
32.
32? Okay. So slide 32 has this image on it, right? And this is the regulation of it, okay? Oh, wow. It's kind of crazy. So I told you how fructose 2,6-bisphosphate was made, right? It was made from PFK2, right? You could make it, and then you can also break it down by fructose 2,6-bisphosphate, right? You can either make it or you can break it down. These two enzymes that make and break down fructose 2,6-bisphosphate are regulated from dephosphorylation and phosphorylation. So what I'm saying is that there's a step prior to all of this. There's a bigger step here. You need to know which enzyme is being activated. So if you activate PFK2, right, then obviously you're going to do fructose 2,6-bisphosphate, activates PFK1, glycolysis. But that comes from phosphorylation and dephosphorylation. So, in her slides, she says that when PFK2 is phosphorylated, do you think it is activated or inactivated?
Activated?
Inactivated. Yeah, I know. It's opposite. When you... Oh, actually, I'm going to put it on the bottom to make it make more sense. I'm going to put it right here. Right? And we are going to make it inactivated right here. Or, I'm sorry. Yeah, inactivated, yeah. Right? So, when we say inactive, maybe even I should make it a little bit more easier to understand. Inactive right here. Right? PFK2 is inactivated when you phosphorylate it. What do you think then is active? Fructose 2,6-bisphosphate is active, right? So, I'll write it right here, active. Okay? This enzyme here is going to be activated. So what did I tell you? What happens if fructose 2,6-bisphosphatase is active? Tell me. What happens? Will PFK1 be activated or PFK1 will be inhibited? Tell me. Just think about it. What could fructose 2? No. You're telling me fructose 2,6-bisphosphatase. It will activate PFK1? No. Remember what fructose 2-bisphosphatase does? It breaks down fructose 2-bisphosphate. I'm telling you that you need to have this. You need this. If you need this, then that means that you need to have PFK2, because PFK2 makes it. So let's even do this, right? PFK2, it makes this compound, right? And if you make this compound, then that means that PFK1 is activated, which means that glycolysis, right? The problem here is that if I have fructose 2,6-bisphosphate lowering, then that means that enzyme is working on this to lower it, to break it down. It's fructose 2,6-bisphosphatase, right? Which would lower PFK, aka inhibit it. Therefore, you don't do glycolysis, and instead, you'll do gluconeogenesis. Honestly, you should take a picture of this because I think this is going to be pretty helpful in my opinion. Shit, I have so much. Okay, I swear to God, I'm done. I promise. I'm so sorry. It's just so much, and there's a video, and like, I can at least hit it and never have to discuss it again in the review session, okay? That would be crazy. So, what's happening here, to get this to be inactivated, okay? If PFK2 is inactivated, right? If it's inactivated, that means this is activated, right? If PFK2 essentially does glycolysis, right? If it does glycolysis, that means that you have basically enough glucose to do glycolysis, right? Think about it. Glycolysis can only happen if there's a lot of glucose. Now we have to tie in the fact that this enzyme here is actually regulated by hormones, glucagon and insulin, okay? That's why it's a little bit confusing. So the thing here is that, how do you know that you're gonna do PFK2? How do you know that you're gonna do the other enzyme, right? Yes, I know if it's phosphorylated, it's inactivated, but how did it become phosphorylated? Well, obviously, ATP comes into play here, right? DP, right? But to activate this process right here, to activate it, we do glucagon. What does glucagon mean? What do you think glucagon is? When your concentration of, when you have glucagon, it is telling you that blood glucose levels are low. I'll write it right here. Glucagon means that your VGL is low. If blood glucose is low, do you think glycolysis can happen? No. There is not enough glucose to do glycolysis. Glycolysis can't happen, then do you think that PFK1 is activated? No, PFK1 can't be activated, which is why you are going to have PFK2 be inactivated, right? Because I told you that PFK2 causes increase in fructose 2,6-bisphosphate, allows for glycolysis. But if glucagon is saying that you can't do glycolysis, then this enzyme would not be activated. It wouldn't be activated. So we're going to activate fructose 2,6-bisphosphate. What this is saying here is that go do something else, aka go do gluconeogenesis, right? Do you guys get what I'm saying? Does what I say, it doesn't make sense?
Could you draw the top one?
Oh, you want me? Oh, yeah, yeah, yeah.
What's
Okay.
on the top part of this?
Oh, the top part? I
Is
mean,
that F26B being phosphorylated, or is the phosphate just gone?
or maybe I should actually, honestly, thank you for telling me that. I should probably just put it PI.
Okay.
You know that usually PI is, phosphorylation happens when you phosphorylate basically like alcohol groups, so I should probably write that here. My bad. Right? Give me 1 second. I apologize. Thank you so much for bringing that up. Actually, in fact, I'm going to do something else real quickly so that. Okay. So, just like one more time, I swear. So, again, glucagon, you have to understand, means low blood glucose levels. If something has low blood glucose levels, then you cannot do glycolysis. There is not enough glucose to do glycolysis. So, what does that mean? You're going to activate this side here. This kinase, what it does is, is that kinase basically transfers phosphates from high energy compounds like ATP, and it takes the phosphate and it puts it on this like peptide with two enzymes on it, right? Polypeptide chain basically. And when you put the phosphorylate it, you inactivate PFK2, and all of a sudden, fructose 2,6-bisphosphate gets activated. So it's saying that phosphorylation of PFK2 makes it inactive, but phosphorylation of fructose 2,6-bisphosphate makes it active. And if fructose 2,6-bisphosphate is active, this is what's happening, right? This is lowered, PFK1 is lowered, don't do glycolysis, do gluconeogenesis. Evidently saying you don't have enough glucose to do glycolysis, so go make it, right? The last part here is insulin. What does insulin mean regarding blood glucose levels? Yes, exactly. If you're talking about insulin, all it's saying is that there's an increase in blood glucose levels. So if there's an increase in blood glucose levels, don't you think it's possible to do glycolysis? Right? You can take all that glucose and make energy from it. So what we'll do here is we'll say, use a phosphatase, aka add water and take off a phosphate. So we'll we'll hydrolyze this phosphate and take it off. We add water, we take it off. All of a sudden what happens here is PFK2 becomes activated and F2-bisphosphate becomes inactive. What happens if PFK2 is activated? You're gonna make this, fructose 2,6-bisphosphate. If you make fructose 2,6-bisphosphate, you'll do PFK1. It increases. Why are you looking at me like that? Does that not make sense?
Doesn't that mean that both of them are making glycolysis?
How is that possible?
That's a good question. Oh, because one of them is a ACE, that's why. I'm missing the F26 ACE. That's why I was missing. Wait, what?
Is that what you're talking about?
No, I'm saying I was missing what the top one was. Are they both F26 ACE?
Yes.
Oh, I thought. Okay.
Oh God. You were looking at me like I was like speaking a different language. I really think this makes sense. I think this makes sense. Does this make sense to you now?
That helped
Okay.
a lot.
That helped a lot? I'm glad. I'm gonna call it a day. I'm done. Okay? I'm sorry this went over. Hopefully that makes sense. Thank you. Yeah, of course.